one of the important processing technology for the semiconductor is the metal semiconductor junction. That is very important in the sense that ultimately the semiconductor is used for electronic device fabrication, and to switch on an electronic device you must connect it to some electrical supply, say with the battery or some external bias, and that connections are done through some copper wires. So, there must be some contact between the copper wire and the semiconductor. Okay. Now, not necessarily that all contacts will be ohmic in nature, okay, because there are some conditions, some criteria using which we can say whether the contact will be ohmic or non-ohmic type of contact. If it is non-ohmic type of contact, there are many applications of non-ohmic type of contact also. Those contacts are usually known as the Schottky contact or rectifying contact. Okay. As the name implies, the Schottky contact or rectifying contact are the contacts through which current can be passed very easily in one direction, because that is the characteristics of rectifying contact, and it will not allow current to flow in the other direction. Okay. Now, let us see how the contact is made. Here you see that there is a semiconductor piece, and this on the semiconductor piece on the top a metal is deposited, that is the top view. A metal is deposited. Now, this metal is deposited means it can be any metal, it can be say aluminum, it can be gold, it can be platinum, right, any metal, and depending on the nature of the metal is deposited on the semiconductor by the method of say thermal evaporation or electron beam evaporation or say RF sputtering, because it depends on the melting point of the metal, because first you have to melt the metal and then it will be deposited on the semiconductor surface. So, that means for melting say aluminum can be melted easily at say around 300 degrees centigrade in vacuum. If you can make a vacuum of say 10 to the power minus 5 or 10 to the power minus 6 torr, then easily at 300 degrees centigrade the aluminum can be evaporated. It is because of the temperature of the pressure of the vacuum, because normally that melting point is higher, but because of 10 to the power minus 6 torr it can be melted in a lower temperature. But say gold or platinum, that cannot be thermally evaporated because of the high melting point. Even if you apply some vacuum, then also it is not possible. Then you have to use say either electron beam, that means to melt by electron beam, or by RF sputtering. You make the gold target or platinum target, then you sputter the target, and then that can be deposited on the semiconductor surface. So, now by any means you have to deposit the metal on the semiconductor, and this is the planar view. You see that this is the metal, the bluish portion is the metal and it is a semiconductor. Okay. So, that is the piece means which is surrounded by two dashed vertical lines. You see that there are two dashed vertical lines, and in between these two vertical lines you can consider that this is a metal semiconductor junction, a piece from this whole thing is cut and presented here. So, it is a metal semiconductor junction. Now, this metal semiconductor junction have some unique properties. One thing is that when you have a metal, say this is the metal, you know that in metal the Fermi level basically is there, and because of the overlapping of the conduction band and valence band in metal. So, always you find that there are many electrons, even at the surface of the metal you will find many electrons, which is not there in case of semiconductor. There is a concept of Fermi level, and only above Fermi level you can consider that there are some electrons. So, in metal this is, you see that this phi m is the metal work function. When it is multiplied by q, the charge of the electron, the unit becomes electron volt. Otherwise, if you use just phi m, it is in volt. Same magnitude, say phi m is 4. So, phi m can be 4 electron volt if you multiply by q. Otherwise, it is 4 volt if you just use q m, okay, a phi m. So, this phi m is the metal work function, and that is the energy required to emit an electron from the metal surface to the vacuum level. That is the energy which is required to emit an electron from the surface of the metal to the vacuum level. Now, what is the vacuum level?
Where the electron stays free.
Yes, when in vacuum level means there the electron is free from the material, that particular material, it is out of the particular material, and where its kinetic energy is 0. That is an imaginary level we have to consider, that is some reference level. With that reference level we shall discuss the whole thing. Now, this is the n type semiconductor. In this n type semiconductor, you see that this is the conduction bandage, this is valence bandage, and this is the Fermi level leaf, the dotted line. As usual, from the Fermi level to the vacuum level, the energy required to excite an electron from the Fermi level to the vacuum level, it is phi s, or the semiconductor work function. So, when we talk about the work function, it is the energy which is to be supplied to an electron at the Fermi level to excite it from the Fermi level to the vacuum level. It is true for metal also, it is true for semiconductor also. The difference here is that only in semiconductor the surface does not have enough electron to emit. So, we consider the Fermi level to the vacuum level. Here also you can consider that it is the difference between the Fermi level to the vacuum level, because the Fermi level here it is at the surface for semiconductor, it is always there, the free electrons are always available there. Another important parameter is the chi. This chi is known as the electron affinity. Chi is known as the electron affinity. It is the energy required to excite an electron from the conduction bandage of the semiconductor to the vacuum level. So, we see that one is the work function, which is denoted by phi, and that phi can be phi s or phi m depending on whether it is of semiconductor or of metal. Another is the electron affinity, which is known as chi, right. Both are in electron volt if you multiply by q, or both are in volt if you do not multiply it by q. Now, let us take one case where the Fermi level of the metal is greater than the where the work function of the metal is greater than the work function of the semiconductor, being n type. This is case 1. There may be several cases. What are the cases? It may be phi m less than phi s for n type semiconductor. It can be phi m greater than phi s for p type semiconductor. It can be phi m less than phi s for p type semiconductor. That means 4 cases are possible. Either the metal work function can be greater than the semiconductor work function, or the semiconductor work function can be greater than the metal work function. And since 2 types of semiconductors are involved, p type and n type, so it can, there are altogether there will be 4 cases. So, let us take the first case phi m greater than phi s. that means the metal work function is greater than the semiconductor work function for n type material. So, then what will happen? This is an isolated metal in contact with an isolated semiconductor just before the joining. Now, when there will be joining, then what will happen?
Electrons flow from semiconductor to metal.
Yes, when you join it, electrons will flow from the semiconductor to the metal. Why? Because you see that there will be alignment of the Fermi level as well as the vacuum level after contact, and since the metal work function is greater than the semiconductor work function. So, if you compare with the metal surface, there are many more electrons on the conduction band compared to the metal surface, because it is at a higher energy. So, since the electrons here are at higher energy, so they will come down to the metal side. Why? Because they will search for the empty levels. The electrons will search for the empty levels, and there are empty levels above the metal surface. Okay? On the metal side there will be empty levels, because you see that there is a difference. Because of the difference, the electrons will come from the semiconductor side through the metal side. If phi m less than phi s, suppose a case where phi m less than phi s, then what will happen? The reverse thing will happen. Electrons from the metal will go to the semiconductor, because phi m less than phi s means the electrons on the metal side are at higher energy compared to the semiconductor side. So, always the electrons will move from the higher energy side to the lower energy side, and here it is, you see that it is higher energy side, it is lower energy side. So, electrons will move from here to there. Now, during the movement what will happen and how long the movement will continue? It will be like the p-n junction case. In p-n junction case, what we have seen? That electrons diffused from n region to p region and holes diffused from p region to n region. Here you see that there will be no hole diffusion, only the electron will move from the semiconductor side to the metal side. So, that is an interesting difference. There will be no charge transportation from the metal side to the semiconductor side, only there will be charge transportation from the semiconductor to the metal side, because it is at higher potential. Then as the electrons move from semiconductor side to the metal side, so the charges will be accumulated on the metal side, on the metal surface, electrons will be accumulated on the metal surface, and there will be depletion in the semiconductor side, because it is losing electron. So, only uncompensated donors will be left in the semiconductor side. So, at this junction, say this is semiconductor, this is metal, on the metal surface, this is the metal surface, electrons will be deposited, and on the semiconductor side there we can consider a depletion layer of W width, where there will be only uncompensated positively charged donors. And this is the bulk semiconductor. In the bulk semiconductor, it is as usual, it is n type. So, number of electrons is very high. Okay. So, that means now if the vacuum level and the Fermi level aligns, that means if we do have a single Fermi level throughout the material, then what will happen? There you can consider three regions. One region is the metal, one region is the semiconductor bulk, another region is the junction between the metal and semiconductor on the side of the semiconductor, not on the side of the metal. on the side of the semiconductor, where there will be depletion layer. So, that means this is depletion, this is bulk, this is metal. So, you can broadly differentiate among the three different regions. Now, what will happen in the depletion layer? In the depletion layer, the number of electrons is very less. Okay. So, that means E c minus E f, E c minus E f will be large, E c minus E f will be large. Why? Because you see that this is E c, this is E f. When there is a uniform carrier concentration of say 10 to the power 17 per centimeter cube. But if in this region, if it is 10 to the power 10 per centimeter cube, then what you expect? That this Fermi level will be far away from the conduction band edge, right. So, now if you consider this depletion region is nothing but this encircled region, where the charge carriers are few compared to the metal side, compared to the bulk semiconductor side. So, that means this is E c minus E v, it is E c, sorry, it is E c minus E f. This E c minus E f will be large, E c minus E f will be large. So, that means if E c minus E f is large, so the band will bend, and we see that the band bends in this manner, and you see that the bending is up to W, that means the depletion width. Just to cross W, the depletion width, it is again constant, that means E c minus E f is constant. Only the difference in E c minus E f is in this region, It is because of the depletion layer, where the charge carriers are few compared to the bulk region or the metal region. Okay. So, that is very important thing, and we have seen this thing for p-n junction also. In p-n junction also we have seen this thing, but in p-n junction on both sides there was this depletion region. Here only on the semiconductor side there is a depletion region, right. Now, if you consider the band diagram, then we can see that Q b phi n, it is equals to Q phi m minus Q chi for n type. This phi b n is known as the barrier height. This is, you see that this is the barrier height. Which one? This is the barrier height. Barrier height means the energy, height is not here the distance, here it is the energy which is required to excite an electron from the metal to the semiconductor side, right, from the metal to the semiconductor side. Suppose you want to emit an electron from the metal to the semiconductor side, then how much is the energy required? It is phi m, phi b n, that means the barrier height, that is known as the barrier height. Okay. And if one electron moves from the semiconductor to the metal side, how much energy is required? It is B I, that is the built in potential, that we have discussed in case of p-n junction also. It is the built in potential, right. So, these are the two things which are very important if you want emission of electron or movement of electron from semiconductor to the metal side, you need Vi, phi VVI, that means the built in potential. If you want electron to move from the metal to the semiconductor, you need barrier height phi V. So, one thing is the barrier height, another is the VVI or the built in potential. Okay, now, the barrier height from this diagram you see that it is given by phi m minus chi. So, if you know the metal work function and the electron affinity of the semiconductor, you can calculate the barrier height for that metal semiconductor contact. So, what are the parameters you must know? One is the metal work function, it is readily available in the data sheet. For any metal, the work function is available, and chi is the electron affinity of the semiconductors, and this value is also available for the normal semiconducting materials, not very new materials, but people have found out the values for chi also. So, you can see whether this phi m minus chi is what is the value of phi m minus chi, and that is your barrier height for that metal semiconductor contact, right. So, this is for n type. Now, for p type, this q b pi p, that means p means p type and b phi means barrier height, sorry phi, sorry here also it will be q phi b n, sorry here also q phi b p, that is equals to E g minus q phi m minus q chi, it is for p type. For p type it will be this value. Okay. Then if you add these two things, that means barrier height of a material for a particular metal for its both p and n type substrate, then you will get the band gap. If you add these two things, you see that this q phi b n plus q phi b p, this is equals to E g, the band gap. So, that means if you know the band gap and the barrier height for the n type silicon, then for p type silicon the barrier height can be easily determined. Just subtract the value of the barrier height from the band gap of silicon. If the barrier height is say 4 point something, 0.44 and its band gap is 1.12. So, it will be 1.12 minus 0.44. So, 0.6 something the barrier height for the p type silicon for that particular metal. That means, the barrier height changes from metal to metal for a particular semiconductor, and also it changes from semiconductor to semiconductor, because the electron affinity is different for different materials. Now, VBI on the semiconductor side, this is known as the built in potential. What is this? It is an energy seen by the electrons in the conduction band trying to move into the metal, and this V B I is equals to phi B n minus V n. What is V n? Q V n is the energy between the bottom of the conduction band and Fermi level. Okay. So, this is you see that this VPI on the semiconductor side, it is not on the metal side, and it is known as the built in potential. It is seen by the electrons in the conduction band trying to move into the metal, and its value is given by the barrier height minus V n, where V n is the energy between the bottom of the conduction band and the Fermi level. So, this is very important consideration. That means, if you know the metal work function and electron affinity, you can calculate the barrier height, and if you know the barrier height and the position of the Fermi level, you can calculate the built in potential, right. So, this is very important relations. Now, you see that in this view graph, we have seen the barrier height as a function of metal work function for two semiconductors. One is N type silicon, another is N type gallium arsenide. If I change it to P type, the curve will be different. Remember, it is for N type semiconductor. What we see that there are several metals which we have used, say platinum, palladium, gold, nickel, tungsten, aluminum, silver, titanium, hafnium, then magnesium, neodymium. So, different kinds of metals we have used, and it is deposited on N silicon and gallium arsenide. Then the barrier height was measured, and we find the barrier height variation as a function of metal work function. You see that for N gallium arsenide, it is not very widely varied. Why? It is just above 0.5 to it is 0.8, not very high. The variation is not very, it is not stiff, the dependence is not very severe, it is just 0.5 something to 0.7 something. Not that it is varied from 0.1 to 0.1 to 10 or 0.1 to 1, not that, but for N silicon it is better than N gallium arsenide. So, what you find? You find that suppose you use aluminum or silver, the barrier height is almost same. Either you use aluminum or silver, the barrier height is almost same. Similarly, if you use gold or palladium, the barrier height is also almost same, and if you compare the values between these and these, you will find that the value is not very widely differ. There is no wide variation of the values from this point to that point, so far as the gallium arsenide is concerned. Why this thing happen for gallium arsenide? Why this is not found in case of N type silicon? Because for N type silicon, you see that it is say 0.25 to almost 0.9 or 0.95, but for gallium arsenide the variation is not very sharp or steep. Why this thing happens? It happens because of the surface states. One new term I am introducing, it is the surface states. Or the interface states. or the interface states, right. It is either surface states or the interface states, the same thing. As the name implies, states in our subject is the energy levels. States means the energy levels. So, surface or interface states means the energy levels which are due to the surface dangling bonds, and those states are found in the band gap of the gallium arsenide, right. It is because of the surface states. The surface states are found due to the dangling bonds, that means unsaturated bonds at the surface, and it is found in the band gap of gallium arsenide. Any states are found in the band gap, obviously inside the band gap. What those surface states do? These surface states pin the Fermi level. What is pinning of Fermi level? That means, you see that when metal is deposited on the gallium arsenide, there will be a change of Fermi level, that we have seen, there will be a change of Fermi level. But the surface states in gallium arsenide pin the Fermi level. Pin means, suppose you have used a pin to put it on the board, that means you are fixing it on a place. Pinning means you are fixing it to a position. So, surface states compel the Fermi level to be there. That means, Fermi level cannot align itself. Whatever metal you use, because of the pinning of the Fermi level, it is pinning of the Fermi level, that whatever metal you use for gallium arsenide, the barrier height is not improved as per your choice. That is not possible. The barrier height is almost constant. It is because, it is not because of the metal, it is because of the surface states in the gallium arsenide. That is a peculiar situation for gallium arsenide. In many semiconductors it is found, not that it is only for gallium arsenide, but since gallium arsenide and silicon is very well documented material. So, people have seen that for gallium arsenide it happens, whether for silicon it does not happen, right. And this pinning of the Fermi level is there for gallium arsenide. That is why the variation is not very severe in case of gallium arsenide, whatever metal you use. So, that means, if the variation is not wide, then why you will use metals like gold or platinum, because those are very costly. So, just use aluminum or that type of thing, gold, germanium or zinc, etc., that you can use, right. And another problem is that depositing gold and platinum is very difficult also, because of the higher melting point of those materials. Normal thermal evaporation is not possible. So, these are the considerations. That means, suppose you have fabricated one material, you have synthesized one material, that is a new material, the material is say X, it is your material, you have made it. Then contact is required. So, you put many metals on it, silver, gold, platinum, aluminum, etc., and you measure the barrier height. If you find that the change in barrier height with the metal work function is not very severe, then you can consider that for your material X, the Fermi level is pinned. Once Fermi level is pinned, whatever metal you use, the barrier height cannot be changed. Okay. Now, we have started with our Schottky contact. This is Schottky barrier. That barrier height is known as the Schottky barrier, this barrier height. This is the Schottky barrier. Now, it is basically a metal semiconductor contact having large barrier height. Having large barrier height, right. Large barrier height means, what is the meaning of this term large barrier height? That means phi Bn or phi Bp very greater than kT. When you say that this is large in comparison with the value of kT at that temperature, that means if you work at say room temperature, then the value of kT is 26 milli electron volt. So, but the barrier height must be very greater than 26 milli electron volt. If it is there, then you can consider that the barrier is known as the Schottky barrier. And a low doping concentration that is less than the density of states in the conduction band or valence band. Okay. It is low doping concentration, low means less than the density of states in the conduction band or the valence band. What is density of states? Number of empty states per unit volume in the conduction band or in the valence band, where the electrons or holes can be accommodated. So, if your number of states is high and the doping concentration is low, then the Schottky barrier will be there, and at the same time the barrier height must be very greater than the kT. So, these two conditions are there for Schottky barrier. Now, the Schottky barrier can be determined. How the Schottky barrier can be determined? It can be determined either by IV measurements or by CV measurements. Both the measurements will yield the barrier height. Barrier height means phi b. You can calculate from IV, you can calculate from CV, and sometimes we measure phi b using both the techniques and then we compare, and many times we find that the value is different. Phi b obtained from IV measurements, phi b obtained from CV measurements, and phi b from the theoretical value. What is the theoretical value? Phi m minus chi. Theoretical value is phi m minus chi. All the three values are different. There are reasons. One important reason is that you see that the metal is deposited on the surface of the semiconductor, and the surface of the semiconductor is very prone to oxidation. So, before depositing the metal, you have to clean the surface very efficiently, okay? And the surface must be cleaned such a manner that between the metal and the semiconductor no defect, no oxides, nothing, even minute amount of say dust particles is also not there. If it is there, then it will modify the barrier height. right. So, that is important consideration, that sometimes you find that I shall show you an example, that where the barrier height measured from theoretical consideration, that means phi m minus chi, and the barrier height determined from I v or C v is different. It is because of the modification of the surface before the metal deposition. Okay. Now, what are the important differences between p-n junction and metal semiconductor junction? What are the major differences? At least one major difference is there. It is as follows. Say in p-n junction, the current is conducted by both the holes and electrons, because there will be holes and electrons diffusion, and you know that when electron diffuse from n region to p region, it becomes minority carrier. Similarly, when holes move from p region to n region, it is the minority carrier. So, you can say that in a p-n junction, the current is governed by the minority carrier, but in metal semiconductor Schottky junction, the current is controlled by the majority carrier. Current is controlled by the majority carrier, no minority carrier is involved. So, that is why it is the unipolar conduction mechanism. It is unipolar in nature. So, what is the advantage of unipolarity conduction? Yes, yes, the switching time is very less, that means it will be very fast. So, that is why I shall show you that a metal semiconductor Schottky junction is used for fast photodetector is used for fast photodetector response. Photodetector, you know that light when falls on the material, electron and hole pairs are created and proportional current is available on the circuit. So, that is known as the photodetector, that means current proportional to the amount of light which is incident on the surface of the semiconductor.
Photodiode.
Yes, photodiode. Yes, photodiode. So, fast photodiode is obtained from this Schottky barrier devices. So, one thing is that current transport in a Schottky barrier is due to majority carrier and dominant transport mechanism is thermionic emission. Of majority carriers from the semiconductor over the potential barrier into the metal. Okay. So, one is the majority carrier, right, current transport is due to majority carrier, and what is the mechanism? In p-n junction, what is the mechanism? Drift and diffusion. In p-n junction, what was the mechanism of current transport? Drift and diffusion. In Schottky barrier, no, it is a thermionic emission. it is the thermionic emission. It is, we shall prove it, that it is the thermionic emission of majority carriers from the semiconductor over the potential barrier into the metal. Over the potential barrier means the VBI. Now, what is thermionic emission? What is thermionic emission?
Liberation of electrons by thermal means.
Yes. So, now if I show you one view graph, then it will be clear. Yes, you see that the thermionic emission process, current transport can be by various means, particularly for the bulk material it is drift and diffusion etc. And the semiconductor surface, at the semiconductor surface, carriers may recombine with the recombination centers due to the dangling bonds of the surface region, that also we know. In addition to this recombination, if the carriers have sufficient energy, they may be thermionically emitted into the vacuum. If the carriers have sufficient energy, where we are considering the surface, we are considering the surface, not the bulk. So, thermionic emission mechanism is applicable for the surface only. When metal and semiconductors are joined, it is the phenomena which are seen in the surface of the metal and the surface of the semiconductor. Bulk is not involved. That is why diffusion and drift is not there. Okay? In surface you see that what can be there. In surface there can be recombination with recombination center. What is the origin of recombination center? It is the dangling bonds, right. And additionally, apart from recombination, there can be emission from the surface if the carriers have sufficient energy. So, that is known as the thermionic emission process. And you see that suppose this is your semiconductor, it is an n type semiconductor. I have seen that chi is the electron affinity and phi is the semiconductor work function. So, where is the vacuum? Vacuum is above this line, this is the vacuum, because you know what is chi. Chi is the energy required from the conduction bandage to the vacuum, emit an electron from the EC to the vacuum. So, that means if the electron distribution is like this, because we have not calculated the electron distribution in n type semiconductor, that is not required in processing class, that will be discussed thoroughly in your physics class. So, you will find that the distribution will be like this. Okay? It is Gaussian having a tail in the higher energy side. Okay? So, now this is the tail, you find that there are some electrons which are above chi. Some electron means those are due to the thermionic emission. So, thermionic emission is possible in n type semiconductor also. Because of the distribution of electron, you see that most of the electrons will be in the outside inside the vacuum level, but there will be some electrons, a few, not very high. You see that this is the tail region and it is this region is marked with some blue color. You see that this blue color region means it is the thermionically emitted electrons. So, that means when we talk about the thermionic emission, it means that some of the electrons are detached from the semiconductor surface to the vacuum. That means chi energy is required, that is the electron affinity. If you put chi energy, then it is possible. And electron density, that is we have seen that this is the electron distribution, electron density. This electron density can be calculated by this integration, where the lower limit is chi and the upper limit is infinity. Why? Because the lower limit is chi and upper limit is infinity, only those electrons will be available. For conduction band, what we have put here, EC to infinity, you can see we have calculated in the at the beginning of the course. EC means from the bottom of the conduction band to the infinity, but here not from the bottom of the conduction band, because chi energy is the minimum energy required. So, chi to infinity, and this is the expression for the thermionically emitted electron density, where NC is the effective density of states, chi is the electron affinity, Vn is the difference between the bottom of the conduction band and the Fermi level, kT is the thermal energy, K is the Boltzmann constant, T is the temperature in Kelvin. This is the density of effective density of states in the conduction band, because we are considering the electron. So, this is the electron density with energies above chi. Okay. Whatever be the small value, it will be there. Now, with this expression, probably we have write down this expression. You see that if I try to calculate this thing, calculate the thermionically emitted electron density NTH at room temperature for an N type silicon sample with an electron affinity of chi equals to 4.05 electron volt and Vn is 0.2 electron volt. If we reduce the effective chi to 0.6 eV, what is NTH? Calculate the thermionically emitted electron density at room temperature, that means T is 300 K and chi is given, Vn is given. So, what you need? You need NC. What you need? You need NC. You write down the value of NC. You write down the value of NC for it is for N type silicon. So, it is 2.86 into 10 to the power 19, 2.86 into 10 to the power 19 per centimeter cube, that is NC. Okay. And you will find that you can try in your room, you will find that for chi equals to 4.05 electron volt and chi equals to 0.6 electron volt, only two cases are given. Okay. The rest of the things are same, NC is same, Vn is same, everything is same, T is same, K is same. What you expect? What should be the electron density? For this case where chi is 4.05, it is almost 0. For chi equals to 0.6 electron volt, you will find some appreciable amount of electrons moving to the vacuum from the thermionic mechanism. Why? Say this value is 10 to the power 10, say an example. Why? It is very simple. Here the chi is low. So, 0.6 eV energy will give you thermionic emission from the semiconductor to the vacuum level. Here it is very high, 4.05 electron volt energy is very high energy for semiconductor. So, that means it is vacuum level, this is 4.05 electron volt and this is 0.6 electron volt. Which one is favorable for the emission? This one is favorable, because here the energy involvement is very less, only 0.6 electron volt, right. Here it is very high energy. So, at that energy the thermionic emission electron density is almost 0. Here it is an appreciable value. So, you try this numerical problem in your room and you must submit it to me. Today I shall give you one more example numerical problem, you have to submit. It is a requirement for your assessment. Yes. So, what we see that thermionic emission mechanism is the main mechanism for this junction, metal semiconductor junction. Okay. Now, if thermionic emission mechanism is there, in the next class I shall show you what are the current components. At thermal equilibrium, what will happen? At thermal equilibrium, the current, the number of electrons, current due to the number of electrons from the semiconductor side to the metal side. Here you see that it is the semiconductor side to the metal side, okay, or yes, from semiconductor side to the metal side, or from metal side to the semiconductor side by this phi b. Those are equal and opposite. So, at thermal equilibrium there will be no current passing through the junction. Why? One is that E V 0, another is phi b. There are two barriers and they will resist. So, at thermal equilibrium the current from this side to that side or from that side to this side will be same, it will be 0. But what will happen if it is made forward bias? If it is made forward bias, then you see that this VBI reduces. What is the forward biasing? VBI reduces. So, that means now the electrons can surmount the barrier and the flow of current will be from the n type semiconductor to the metal side. You see that it is the forward biasing. In this junction, forward biasing means metal is at a higher potential compared to the semiconductor. Why? Because the semiconductor is n type. Because the semiconductor is n type. So, you see that there will be positive potential connected to the metal to make it forward bias. Because semiconductor is n type, always the negative terminal of the battery must be connected with the n type semiconductor. So, that means it is reduced, reduced means earlier it was V B 0 or V B I, now it is E V 0 minus B, because we discussed earlier that the voltage will be dropped in the depletion region only, because the resistance is high in the depletion region. So, the depletion region will be narrowed down or V B 0 will be less, and so the electrons will move from semiconductor to the metal side and you will get the current. Okay. So, in the next class we shall consider those things. Thank you.